Welcome to this rigorous scientific lecture on the discovery of superconductivity. Today, we will walk through the experimental workflow that led to one of the most remarkable discoveries in condensed matter physics. In 1911, Kamerlingh Onnes at Leiden University made a groundbreaking discovery while measuring the electrical resistance of mercury at cryogenic temperatures. He observed something completely unexpected. The resistance dropped to zero at a specific temperature. The fundamental question Onnes was investigating was, how does electrical resistance behave as we approach absolute zero temperature? At the time, there were competing theories. Some predicted resistance would gradually decrease. Others predicted it might increase due to electron scattering. Let's begin with the first step of our experimental workflow. We need to perform high-resolution resistance versus temperature measurements. This requires cooling a sample systematically while continuously monitoring its electrical resistance. Here is our experimental setup. We have a mercury sample immersed in a liquid helium bath. We pass a known current through the sample and measure the voltage drop using a 4-point probe configuration to eliminate contact resistance effects. The 4-point probe method is absolutely critical. By using separate current and voltage leads, we measure only the resistance of the sample itself, not the resistance of the electrical contacts. This is essential for accurate measurements. The resistance is simply the measured voltage divided by the applied current. Ohm's law. Let me emphasize why controlling for contact resistance is so important. If we used a 2-point measurement, we would measure the total resistance, including the contacts. In a 2-point setup, the measured resistance equals the sample resistance plus twice the contact resistance, because we have two contacts in series. Contact resistance can easily be several ohms, while the sample resistance we're trying to measure might be milliohms or micro-ohms. The contact resistance would completely dominate our measurement and obscure the superconducting transition. In the 4-point method, the current flows through the outer two contacts, and we measure voltage across the inner two contacts. Since the voltmeter has extremely high input impedance, essentially no current flows through the voltage leads, so there's no voltage drop across those contacts. Now let's discuss the temperature sweep protocol. We need to cool the sample slowly and systematically, taking resistance measurements at closely spaced temperature intervals. We plot resistance on the vertical axis versus temperature on the horizontal axis. Let me show you what the data looks like as we cool the sample. This is the remarkable result. Above 4.2 Kelvin, the resistance is constant at about 0.25 ohms. But at exactly 4.2 Kelvin, the resistance drops discontinuously to zero. Not just very small, but actually zero within measurement precision. The transition is extraordinarily sharp. The resistance drops from its normal value to zero over a temperature range of less than 0.01 Kelvin. This is not a gradual change, it's essentially a discontinuous jump. Now you might ask, could this be a measurement artifact? Could there be something wrong with our experimental setup that makes it look like the resistance is zero when it's really not? Excellent question. This is exactly what good experimentalists must consider. Onnes performed multiple tests to rule out artifacts. He verified that changing the current didn't affect the result. He checked the voltage measurement system. He tried different samples. The zero resistance was real. Step 4 is to repeat the measurement with both warming and cooling cycles. This tests whether the transition is reversible and reveals any hysteresis in the phase transition. In the cooling cycle, we decrease the temperature slowly from above the transition temperature to below it, recording resistance continuously. In the warming cycle, we do the reverse. Start below the transition temperature and slowly increase temperature back up. Here we see both cycles. The green curve is cooling, the red curve is warming. Notice there's a small hysteresis. The transition occurs at a slightly different temperature, depending on whether we're cooling or warming. This is characteristic of a first-order phase transition. For mercury, the hysteresis width is typically 0.05 to 0.1 Kelvin. This small hysteresis tells us about the thermodynamic nature of the transition and suggests metastable states can exist near the critical temperature. What causes this hysteresis? Why doesn't the transition occur at exactly the same temperature in both directions? The answer involves nucleation barriers and thermal lag. When warming from the superconducting state, the sample can remain superconducting slightly above the equilibrium transition temperature, because there's an energy barrier to nucleating the normal phase. Similarly, when cooling, thermal gradients and nucleation kinetics can shift the observed transition temperature. Step 5 is to carefully analyze the sharpness of the transition. We need to quantify just how abrupt the resistance change is. We define the transition width as the temperature range over which the resistance drops from 90% of the normal state value to 10%. For high-quality mercury samples, this width is less than 0.01 Kelvin. Let's put this in perspective. If our sample is 1 centimeter long and the transition width is 0.01 Kelvin, we can estimate the spatial width of the transition region. If we have a typical temperature gradient of 0.1 Kelvin per centimeter, then the spatial width of the transition region is about 0.1 millimeters. This is remarkably sharp on a macroscopic scale. Based on these observations, we can propose that superconductivity is a thermodynamic phase transition. Let's think about what this means. What are the characteristics we observe that suggest a phase transition? First, we have a discontinuous change in a physical property. The resistance drops abruptly to zero. Second, the transition occurs at a well-defined critical temperature that is reproducible and characteristic of the material. Third, the small hysteresis suggests first-order character, though we'll later learn that superconductivity is actually a second-order phase transition in zero magnetic field. Let's develop a simple thermodynamic description using free energy. Near the transition, we can expand the Gibbs free energy in terms of an order parameter. We write the Gibbs free energy as G of T equals G sub n plus alpha times T minus T sub C times the magnitude of psi squared plus beta times the magnitude of psi to the fourth. Here psi is the superconducting order parameter. The order parameter psi is 0 in the normal state above T sub C and becomes non-zero in the superconducting state below T sub circa. It describes the macroscopic quantum wave function of the superconducting electron pairs. To find the equilibrium state, we minimize the free energy with respect to the order parameter. Taking the partial derivative and setting it to 0 gives us the equilibrium condition. Solving this, we find that the magnitude of psi squared equals alpha times T sub C minus T divided by 2 beta, valid for temperatures below T sub circa. Above T sub C, psi equals 0. Now comes the crucial validation step. If superconductivity is truly a phase transition, we should be able to predict other critical parameters. One key prediction is the existence of a critical magnetic field. What should happen if we apply an external magnetic field to a superconductor? Can it remain superconducting in arbitrarily strong fields? The answer is no. A sufficiently strong magnetic field will destroy superconductivity. There exists a critical field H sub C, above which the normal state becomes energetically favorable. When we apply a weak magnetic field to a superconductor, screening currents flow on the surface that perfectly cancel the field inside the bulk. This is the Meissner effect. But these screening currents cost energy. The critical field depends on temperature. Near T sub C, it follows approximately H sub C of T equals H0 times the quantity 1 minus T squared over T sub C squared. Here, H0 is the critical field at 0 temperature. For mercury, H0 is approximately 0.041 Tesla, and T sub C is 4.2 Kelvin. These are material-specific parameters. To validate this prediction, we perform a new experiment. We fix the temperature below T sub C and measure resistance as a function of applied magnetic field. This is the result at 3 Kelvin. Below the critical field of 0.035 Tesla, the resistance is 0. Above this field, the resistance jumps to the normal state value. The transition is again very sharp, confirming our phase transition model. Let's do a quick back-of-the-envelope calculation to understand the energy scales involved. The energy cost of excluding a magnetic field from a volume 5 is approximately b squared over 2 mu 0 times the volume. This is the magnetic field energy density times the volume. The condensation energy, the energy gained by forming the superconducting state, scales as n times k sub b times t sub c, where n is the number of electrons involved, and k sub b is Boltzmann's constant. At the critical field h sub c, these two energies balance exactly. Below h sub c, the condensation energy wins, and the superconducting state is stable. Above h sub c, the field energy is too large, and the normal state is favored. We can write this balance as h sub c squared over 2 mu 0 equals 1/2 gamma T sub c squared, where gamma is the Sommerfeld coefficient representing the electronic specific heat. For mercury, let's plug in numbers. H sub c is 0.041 Tesla at 0 Kelvin. This gives a magnetic energy density of about 670 joules per cubic meter. 0.041 squared divided by 2 times 4 pi times 10 to the minus 7, which equals approximately 670 joules per cubic meter. This is the condensation energy density. Another key prediction from the phase transition model is the existence of a critical current. If we pass too much current through a superconductor, it should revert to the normal state. When current flows through a superconductor, it creates a self-field at the surface. This self-field adds to any external field. For a cylindrical wire, the self-field at the surface is H self equals I over 2 pi r, where I is the current, and r is the wire radius. The critical current occurs when the self-field reaches the critical field. So I sub c equals 2 pi r times H sub c. Let's take a concrete example. If we have a mercury wire with radius 1 millimeter and critical field 0.04 Tesla, what's the critical current? I sub c equals 2 pi times 10 to the minus 3 times 0.04, which equals 0.25 amperes. So this wire can carry up to 250 milliamperes before losing superconductivity. We test this by measuring resistance versus current at a fixed temperature below T sub c. Perfect agreement. Below 0.25 amperes, resistance is 0. Above this current, resistance appears. This validates our phase transition model and the predicted scaling between critical field and critical current. Now let's map out how all the critical parameters depend on temperature. This gives us the complete phase diagram. Here is the phase diagram. The curve shows the critical field as a function of temperature. Below the curve, the material is superconducting. Above the curve, it's in the normal state. The curve goes to 0 at T sub c and reaches its maximum H0 at 0 temperature. This parabolic shape, approximately 1 minus T squared over T sub c squared, is universal for type 1 superconductors like mercury, lead, and aluminum. The final step in our workflow is to verify reproducibility and study different materials to understand what determines T sub c. Different materials have different critical temperatures. Mercury has T sub c equals 4.2 Kelvin. Lead has T sub c equals 7.2 Kelvin. Niobium has T sub c equals 9.2 Kelvin. What determines the critical temperature for a given material? Why is lead's T sub c higher than mercury's? The answer, which came from BCS theory in 1957, is that T sub c depends on the strength of electron-phonon coupling. Materials with stronger coupling between electrons and lattice vibrations have higher critical temperatures. BCS theory gives us T sub c proportional to theta sub d times the exponential of -1 over lambda times n of E sub f. Here, theta sub d is the Debye temperature, lambda is the coupling constant, and n of E sub f is the density of states at the Fermi level. This remarkable formula connects microscopic properties of the material, like its phonon spectrum and electronic structure, to the macroscopic critical temperature we measure in our resistance experiments. One beautiful piece of evidence for phonon involvement is the isotope effect. If we replace mercury atoms with heavier isotopes, the critical temperature changes. The critical temperature scales as T sub c proportional to m to the minus alpha, where m is the isotopic mass, and alpha is approximately 0.5 for most superconductors. This proves that lattice vibrations, whose frequency scales as 1 over square root of m, are essential. For mercury, if we use mercury 198 versus mercury 204, which differ in mass by about 3%, we observe a T sub c difference of about 0.06 Kelvin. This is exactly what the BCS theory predicts. Let's discuss the practical implications of these measurements for precision and reproducibility. The critical temperature is an intrinsic property of the pure material. For high purity samples, it can be determined to within 0.001 Kelvin. This makes superconducting transitions useful as temperature calibration standards. The transition width, however, depends on sample quality. Impurities, defects, and inhomogeneities broaden the transition. A high-quality sample shows a sharper transition. The transition width scales approximately as the square root of the impurity concentration. This is because different regions of the sample have slightly different local T sub C values due to compositional variations. Before we conclude, let me briefly mention an important distinction that emerged later: Type 1 versus Type 2 superconductors. Type 1 superconductors, like mercury and lead, show complete flux expulsion below a single critical field H sub circa. Above H sub C, they become completely normal. Type 2 superconductors, like niobium-titanium alloys, have two critical fields. Between H sub C1 and H sub C2, they're in a mixed state, where magnetic flux partially penetrates in quantized vortices. Here's a comparison. Type 1 superconductors have one critical field separating the Meissner state from the normal state. Type 2 superconductors have two critical fields with a mixed vortex state in between. Type 2 superconductors are crucial for high-field applications like MRI magnets and particle accelerators because H sub C2 can be extremely high, tens of Teslas or more. Let's summarize what we've learned about the discovery process and the scientific method in action. First, systematic measurement with proper experimental controls. The 4-point probe method was essential to eliminate artifacts. Second, reproducibility through multiple warming and cooling cycles. This confirmed the transition was a real material property, not an artifact. Third, the sharp transition width suggested a thermodynamic phase transition rather than a gradual crossover. Fourth, proposing the phase transition model allowed us to make testable predictions about critical fields and critical currents. Fifth, validation through independent experiments confirmed the model and revealed new physics. Let me give you the key experimental parameters for mercury that you should remember. Critical temperature. T sub C equals 4.15 Kelvin. Critical field at zero temperature. H sub C of 0 equals 0.041 Tesla. Transition width for pure samples. Less than 0.01 Kelvin. London penetration depth. Approximately 40 nanometers. This is how far magnetic fields penetrate into the surface. Coherence length. Approximately 30 nanometers. This is the size of a Cooper pair. The discovery workflow we've discussed isn't just historical. It's still used today for characterizing new superconducting materials. When high-temperature cuprate superconductors were discovered in 1986, researchers used exactly the same measurement principles: careful resistance versus temperature sweeps, controlling for contact resistance, mapping out phase diagrams. Iron-based superconductors, discovered in 2008, were characterized the same way. The experimental workflow is universal. How has technology improved these measurements since Onnes's time? Modern cryostats allow temperature control to 0.0001 Kelvin. Modern voltmeters can measure nanovolts. This lets us resolve transition widths that Onnes could never see. Digital data acquisition systems can take thousands of data points per second, enabling rapid mapping of entire phase diagrams in a single cooldown. Let me close with a thought about the beauty of phase transitions in physics. Superconductivity is macroscopic quantum coherence. 1 billion trillion electrons, 10 to the 23 particles, all acting in perfect unison, described by a single quantum wave function. It's an example of spontaneous symmetry breaking. Below T sub C, the electromagnetic gauge symmetry is broken, giving the photon an effective mass inside the superconductor. It's an emergent phenomenon. You cannot predict superconductivity by studying a single electron. It emerges from the collective behavior of many interacting particles. This is why careful experimental characterization matters so much. Only through systematic measurement can we discover and understand these remarkable collective phenomena. In conclusion, the discovery of superconductivity exemplifies the scientific method at its best. Precise measurement reveals unexpected phenomena that challenge our understanding. Systematic characterization identifies key signatures like phase transition behavior. Theoretical models make testable predictions that guide further experiments. Validation and extension lead to deeper understanding and eventually to applications. The workflow we discussed, from resistance sweeps to phase diagram mapping, remains the gold standard for characterizing superconductors over a century after Onnes' discovery.